Despite the title, this is really a talk about Carnap. What I want to talk about today are some of the ways, indeed one way in particular, in which I take it Carnap really rejects a fundamental view of his teacher Frege about the nature of logic and mathematics. And in particular, what I want to talk about is the extent to which Carnap rejects Frege's idea that what grounds the logical relations are relations between thoughts or contents. And of course, I take it that the rejection of this is a large part of the project of the logical syntax of language. And so what I want to talk about is a particular kind of reason to reject Carnap's kind of view. And this argument against a Carnap approach to logic, I think we find both in Frege and in Gödel. Now, of course, this is a little bit anachronistic to attribute such an argument to Frege, but I do think there's a line of reasoning that we see in Frege that's very similar to a line of reasoning that we find in that paper of Gödel's called Is Mathematics Syntax of Language, the paper that was intended for the Schilp volume. And so what I'm going to do today is first highlight just a couple of points about Carnap's project in logical syntax of language that I'd like to focus on, and then look at a line of reasoning that we find in Frege all over the place. This won't be surprising to anybody who's read any Frege. And then take a slightly more careful look at some of the text of that Gödel essay. And what I'm going to suggest is that there's an aspect of the argument in Gödel's essay that's perhaps been underappreciated that I think is actually better maybe than it is often taken to be. And I think, from what I understand about the people in the audience whose work I know, I think that everybody will disagree with me. So I think this is a really good audience for me. All right, so to begin with, so this is, all of the quotations from Carnap are from syntax. And this is from section 1, I believe. So the development of logic during the past 10 years has shown clearly that it can only be studied with any degree of accuracy when it's based not on judgments, thoughts, or the content of thoughts, but rather on linguistic expressions, because only for them is it possible to lay down sharply defined rules. I hope we see already the ways in which this is a real rejection of what Frege thinks about logic. But even those modern logicians who agree with us in our opinion that logic is concerned with sentences are yet for the most part convinced that logic is equally concerned with the relations of meaning between sentences. They consider that in contrast with the rules of syntax, the rules of logic are non-formal. In the following pages, in opposition to this standpoint, the view that logic too is concerned with the formal treatments of sentences will be presented and developed. And let me be clear, I take it logic too. The point is logic is like syntax, right, in just being concerned with the formal treatments of sentences. It's not concerned with the meanings of sentences. So I take it that what's going on here is a rejection of the Fregean view that what justifies the use of a particular formal system is that the rules of inference and axioms of that formal system reflect the pre-existing rules of entailment that hold between the thoughts expressed by the sentences of that system. For Carnap, of course, there isn't any sense of justification of the rules. And there isn't any sense in which the logic that we're looking at when we look at the syntax of the language is in any sense reflecting a pre-theoretic relationship of entailment that holds between thoughts. All of that is out the window. So as Carnap puts it later on in syntax in section 84, his claim is that there's a sense in which both formalism and logicism are correct. You'll probably all remember these passages. The formalist view, he says, is right in holding that the construction of the system can be effected purely formally, that is to say, without reference to the meaning of the symbols, and that, I take it, is the project. And this is going to be a theme throughout the rest of what I talk about today. What I'm going to be talking about with respect to this objection, as I'm calling it, that I find, that I think we find in both Frege and Gödel, is the role of the applications of mathematics. So as everybody who's read Frege remembers, for Frege, one of the problems with any kind of formalism, and I think this will apply to the syntax project, is that it doesn't make the right account of, it doesn't give any account of how it is that mathematics can be applied. So what I want to talk about very, very briefly before turning to Frege and Gödel is the account of applications of mathematics, that is, applications of mathematical reasoning to the empirical realm that we find, I think, in syntax. And so here's Carnap again. The system must contain general rules of formation concerning the occurrence of the mathematical symbols in synthetic descriptive sentences also, right? So physics. Together with consequence rules for such sentences. Only in this way is the application of mathematics, i.e. calculation with numbers of empirical objects and with measures of empirical magnitudes, rendered possible and systematized. And a structure of this kind, okay, so a structure of this kind, I take it, is, roughly speaking, a language, a framework like language 1 or language 2, when supplemented with a material interpretation. And so we've got a bunch of rules of the system, we've got a materially interpreted bunch of bits of the language, and in the end we have sentences, some of which are going to be mathematical and some of which are going to be empirical. The dividing line doesn't need to be sharp, but it often is, depending on how the rules of the system work out. But the idea is that we've got a materially interpreted framework, we have mathematical sentences, and the relationships between those sentences and the synthetic descriptive sentences is what makes mathematics applicable, right? So we can deduce relationships between, so I have an empirical generalization, I have a mathematical sentence, I put those two together, and by the rules of the system, I deduce from them a synthetic descriptive sentence, which gives me, let's say, a prediction about what's going to happen. And that's what the mathematics does for us. It's a nice tool for getting from synthetic to synthetic sentences. So let me just read this to you. A structure of this kind fulfills simultaneously the demands of both formalism and logicism. For on the one hand, the procedure is a purely formal one. Why? Because the rules of the system are just laid down, syntactic, arbitrarily chosen. And on the other, the meaning of the mathematical symbols is established. How? By their syntactically defined relationships to one another and to the synthetic descriptive sentences. And thereby the application of mathematics in actual science is made possible, namely by the inclusion of the mathematical calculus in the total language. Okay, so there's, I take it, the syntax picture of the applications of mathematics. Okay. So I want to stress here then the idea that, that what's going on with these laws of mathematics and of logic, and I'll just use those notions interchangeably, it's logicism after all, right? What's going on here is that they're arbitrarily chosen, they're not justified in any way, they're purely syntactic, purely formal. They have the right deductive relationships to the synthetic sentences, and that's how we get applications out. Okay, now let me shift gears and talk about Frege for a moment. So this is from Grundgesetze Volume 2. He's, of course, not here talking about Carnap. He's talking about probably a more crude form of formalism. But I think the objections that he's going to make here are going to be at least instructive. So we too, says Frege, could have introduced our rules of inference and the other laws of the concept script, that is to say his deductive system, the Begriffsschrift, as arbitrary stipulations without ever speaking of the reference and the sense of the signs. Right? We could have done that. We didn't, of course. What we took to be an external representation of an inference would then be comparable to a move in chess, the mere transition from one configuration of chess pieces to another, without any transition from one thought to another corresponding to it. So we could, in fact, have done what Carnap does, right? But without a thought content, no application will be possible, says Frege. How could an equation which expressed nothing, which was nothing but a group of figures that could be transformed according to certain rules into other groups of figures, be applied? Now, it's applicability alone which elevates arithmetic above a game to the rank of a science. The applicability thus necessarily belongs to it. Okay, so this is the beginning of what he says over and over again, which is if you're going to be a formalist, you can't make sense of the applications of science. I want now to look at a passage that comes from an essay called On Formalist Theories of Arithmetic from 1885. From Frege, again, in which Frege is discussing something which, again, is not quite Carnap, but I think is importantly similar. So here's the proposal that Frege is discussing in the text we're about to look at. It's the proposal that the only meaningful parts of mathematics are those parts that deal with the natural numbers. That the rest of mathematics is an instrumental, formal, syntactically defined add-on. Instrumental in this sense, in exactly Carnap's sense, instrumental in the sense that those other parts of mathematics are just rules that we use to get from sentences of the meaningful mathematics to sentences of the meaningful mathematics, with the in-between transitions not being meaningful, just being useful. Okay, so that's the proposal that Frege is thinking about here. This, of course, is not Carnap's proposal, but I hope the parallels are similar. I mean, I hope the parallels are clear. So what about, as I say in the title here, what about an instrumentalist approach to the mathematical sentences? So here's Frege on a closely related proposal. One could say, says Frege, and he here characterizes the approach, we merely stipulate rules in accordance with which one can move from given equations to new ones, just as one can give rules for moving chess pieces. Unless an equation contains only positive numbers, it no more has sense than the position of chess pieces expresses a truth. Now, in virtue of these rules, it may happen that an equation of positive whole numbers does finally occur. And this is the proposal he's still sketching out, right? And if the rules are of such a kind that if one has started with true equations, right, the contentful true ones, they can never lead to false conclusions, then only two cases are possible. Either the final equation is senseless, so for example, it's about irrational numbers, let's say, or it has a content about which we can pass judgment. This last will always be the case if it contains only positive whole numbers, and then it must be true, for it cannot be false. Okay, so that's the proposal he's just sketched out. We use the rules of, as it were, non-natural number mathematics to get from contentful natural number mathematics to contentful natural number mathematics, and we have in the background the assumption that this procedure, these rules, will get us from truths to truths. And Frege's question then is, the only question is, how the rules are to be arranged so that nothing false ever results, right? I mean, the fact that you just have randomly stipulated rules doesn't give you any guarantee that if you start with true contentful sentences, you will get out at the end true contentful sentences. You need to know something about the rules of manipulation that you've stipulated. One might say something like this. Okay, so here's going to be the continuation of his characterization of the proposal he's attacking. One might say this: if these rules contain no contradictions among themselves, these are the arbitrarily stipulated rules, and do not contradict the rules of positive whole numbers, that's the contentful part of mathematics, then no matter how often they are applied, no contradiction can ever enter in. So you've got a background consistency guarantee of some kind. Consequently, if the final equation has any sense at all, it must also be non-contradictory and hence be true. Okay, so that's the proposal, that the guarantee that if you start with contentful true claims and you use the rules in question, you'll end up with contentful true claims. The guarantee is that the rules are consistent. Against this, Frege has two worries. Already this last is a mistake, for a proposition may very well be non-contradictory without being true. Okay, so the first worry is that the fact that your rules don't allow you to prove a contradiction from true claims doesn't mean that they will only allow you to prove true claims from true claims. Let me pause here for a moment to say something about the parallel that I want to emphasize between Carnap's own proposal in syntax and the proposal that Frege is about to criticize. I take it that, well, I would like not to suppose that Carnap is interested in true sentences in a sense in which he's often taken not to suppose that there is some pre-linguistic, pre-theoretic notion of truth. But Carnap does think that there are applied sentences that are the ones that we, as it were, want to get to in the end. The synthetic descriptive sentences that are part of our overall framework, if it's a good framework that we get out at the end, that is the ones that we get by applying mathematics to empirically verified generalizations, ought to be the kinds of synthetic descriptive sentences that are going to be empirically confirmed, right? They ought not to be the things that turn out to be disconfirmed all over the place. So a good framework will be one in which the synthetic descriptive sentences that you get out at the end via the use of mathematics are, let's just say, good in whatever way we think of good. I think empirically confirmed or likely to be empirically confirmed is a good way to think of it. That notion of goodness is what's the parallel, as it were, of the notion of truth here that Frege is talking about, right? So for Frege, you start out with good content, for the proposal he's criticizing, start out with good contentful sentences, apply contentless mathematics with some guarantee that you're doing this in a good way, and you end up with good contentful sentences at the end. Similarly, for the logical syntax of language project, you start out with empirical generalizations, you apply the content-free mathematics, and you get good synthetic descriptive sentences out at the end. Okay, so Frege says there are going to be two problems here. The first problem is that it's not at all clear that a consistency proof is sufficient. Right? Why? Because a proposition may very well be non-contradictory without being true.
Can I ask a quick question?
Yeah, Steve.
Is he talking about atomic arithmetical sentences? About
Not necessarily.
Because it looked like it before. He said something.
I don't think they need to be atomic.
For such sentences.
Then you might think, depending on how rich your axioms are at the beginning, you may well think, well, look, you're either going to prove 0 equals 1 or you're going to prove it's not. And so if it's consistent, then. So in the general sense in which he's criticizing the proposal, I think First of all, he's not making any assumptions about what your axioms are going to look like. So they might be extremely partial, right? You might not get a complete list out. And we're also not necessarily talking about atomic sentences. But yeah, nice point. Depending on what the rules of the system look like, it may well be that consistency is close to all you need.
You're talking about a kind of basis of test sentences. And then
Something like that.
standard ideal sentences.
Yeah, something like that. I think that's right. Yeah. Okay, non-contradictoriness therefore does not suffice. And even if it did, it would first have to be proved. His point here is that contradictions are not always evident, but instead are often brought to light only by a series of inferences. And here he's just criticizing the idea that you would notice inconsistency if it were there. So let me just try and give a quick summary of what I take as, for me, the important point here. Frege's objection to the instrumentalist account of rules of proof. We would need, in addition to the rules, some guarantee that the right, so maybe applied, maybe contentful, mathematical, however you want to think of it, that the right final sentences are generated by them. This would require, first of all, a consistency proof, and secondly, probably more. Let me just back up and point out that Frege's worries about consistency proofs are not the same as our worries about consistency proofs. First of all, this is, well, it's published in 1903, probably written in about 1893, long before we've got any clear worries about incompleteness. Frege also thinks of consistency in ways that are slightly different from the ways in which you and I and Hilbert might think about consistency. Nevertheless, Frege does think that there are real difficulties that stand in the way of giving consistency proofs. And so that's something that unites Frege and Gödel. It's just that the reasons for thinking that there are difficulties are radically different. And I can say more about that later if you want, but that won't be crucial. And also, in Frege's view, you need not just a consistency proof. And this is, again, a consistency proof for those arbitrary, stipulated, formalistic, syntactic rules that are purely instrumental. And you would need more. Okay, so that's what I want you to have in the background as the Frege stuff. Okay, let's move to Gödel's essay. And so this is the essay that was, in some sense, intended for the Schilp volume. I suppose actions and intentions don't always come together. I take it was intended but not published. It's now in the third volume of Gödel's collected works. There are, I think, a number of different objections floating around in this essay. There are two in particular that I want to talk about. The first one I want to skim over quite lightly. It's been discussed a good deal in the literature. I want to say something about the objection and something about a response to that objection given by Tom Ricketts, because it's going to be important then to what we say about the second objection. And it's the second objection I actually care about today. Okay, so the first objection that Gödel raises is as follows. This comes from what's in the I'm going to take the version of this essay that appears in the third volume to be the canonical version, and these are the section numbers from that version. Okay. A rule can be called syntactical only if it's clear from its formulation, or if it somehow can be known beforehand that it does not imply the truth or falsehood of any factual sentence. This requirement follows from the conception of a convention. The requirement under discussion implies that the rules of syntax must be demonstrably consistent. Okay, so the idea here is he's taking Carnap to be defending the view that mathematical rules are conventional, and to have in the background an idea of what conventional means, such that a rule is clearly not conventional if it implies the truth of any factual sentence. So therefore, in order to defend the view that the rules of mathematics are conventional, you'd better know that they're consistent. Why? Because if they're inconsistent, then they do, in fact, imply factual sentences, of course, because they imply everything. The objection continues, and because the principles used in the proof of consistency must be finitary, this comes from Gödel's conception of what it would take to really make sense of the claim that the rules follow from the syntactic stipulations made, right? Follow in a non-question begging way, right? They can't follow, mathematics can't follow in a way that employs mathematics itself. They have to follow in a fairly straightforward way that just employs the rules given in the stipulated syntactic rules. Okay, and this is impossible, assuming we're trying to preserve all of classical mathematics. Okay, so a summary of that objection. Carnap needs to show that the rules that he has stipulated, right, the rules of mathematics, are really conventional, i.e. they don't imply factual sentences, and this requires an impossible consistency proof. Tom Ricketts has written a good deal about this, as have other people, but there's a nice version of this response in Ricketts' 1994 essay, which is to point out that Carnap really is not, though he talks about convention, he doesn't seem to be relying on some language framework independent notion of conventionality or of factual. What makes the rules of, let's say, language 1 or language 2 in syntax conventional is that they are the rules of the system, period, end of story. they are still the rules of the system, even if they're not consistent. And that will make that system, as Ricketts argues, well, not a very nice system to use, but it's still a system. It has a pragmatic defect, a big pragmatic defect to be sure. But the point is that you don't need to know that the rules are consistent in order to know that they are the rules of the system. And that's all you need to know in order to know that they are, in the relevant sense, conventions, syntactic conventions. So as Ricketts puts it in my paraphrase, Carnap does not in fact rely on any pre-theoretic or language-independent notion of the conventional or the factual. Indeed, he rejects these. All that's required for the syntax project is that the mathematical rules are in fact rules of the system, and that's immediate. They're just stipulated. All right. I actually, to be honest, I think there is more to Gödel's objection here than Ricketts has responded to. And let me just briefly say something about that, though this won't be crucial to what follows. It does seem to me that it's essential to Carnap that he is establishing some crucial difference between rules of mathematics and synthetic descriptive sentences of, let's say, biology or physics. And it seems to me that you want to know that your system preserves such a difference in order to know that the rules of the system are in fact, well, in order to know that you've characterized a system in which mathematics is really different from physics. So whether you call it the difference between the conventional and the not, or the factual and the not, there's some difference here. And if your system isn't consistent, then it's not just pragmatically bad, it's also a system in which there isn't any interesting difference between the mathematics and the physics. Okay, that's an aside. This slide probably shouldn't be here after yesterday, but since it's here, so I'm passing over a number of related objections to Carnap, in particular one that I, up until yesterday, quite liked, Michael Friedman's argument that the need for a rich meta-language in order to describe, to deal with, to compare the syntax of the system conflicts with the neutrality required by the principle of tolerance. This should now say Friedman star, because I believe this is not the actual Friedman anymore. Is this true?
No, it's not the actual Friedman.
Okay.
So it is the actual, but the other.
Okay, good. It should be, yes, the younger, less mature Friedman. Okay, this is really what I care about. What I'm calling objection number 2, and here it is. Carnap's system requires, says Gödel, 1, that the formal axioms and the procedures of proof of mathematics can be deduced from suitably chosen rules of syntax, and 2, that the conclusions as to ascertainable facts, okay, these are the applied conclusions, which are obtained by applying mathematical theorems, and which formerly, that is, by those of us who are realists about mathematics, right, which formerly were based on the intuitive truth of the mathematical axioms, can be justified by syntactical considerations. Let me just emphasize that what I care about here is that is Gödel's claim that the conclusions as to ascertainable facts are justified by syntactical considerations. It's that for Gödel, as I hope will become clear as we go through the next several slides, what's important when you're trying to account for the applications of mathematics is not just that your framework entails, has the resources for making the right implications between sentences, but in fact that when you've given a proof, given a mathematical proof within that system, you thereby have a reason to expect a certain empirical result. You have a justification for a prediction. And that he thinks you don't get out of the syntax project. And this is really what I want to emphasize in the next few slides. This second item, right, so number 2 there, that the conclusions as to ascertainable facts can be justified, right, again requires a consistency proof for the syntactical rules. And why it does will become, I hope, clearer when we look at Gödel's own example. This example comes just following this. As he says, as becomes clear from the following examples. And the first one is this. If mathematics is interpreted to be a system of objectively true propositions, okay, Gödel's own view, then, for example, on the grounds of a proof for Goldbach's conjecture, the claim that every even number is the sum of 2 primes, it can be predicted that a computing machine, which is empirically known to work reliably, will find 2 primes whose sum is some given large number n. In order to make the same prediction for every n, if mathematics is interpreted syntactically, the consistency of the rules of syntax must be known. So let me say something about this setup here. So we've got a machine that we have good reason to believe is reliable. Perhaps we've programmed it ourselves, or perhaps we've watched it in action, whatever. And this is a machine such that if you plug in a number, let's say, it gives as output 2 prime numbers if those prime numbers sum to your input, and gives you 0 otherwise. Right? If we have a proof of Goldbach's conjecture, if we're realists about mathematics, then a proof of Goldbach's conjecture gives us reason to suppose that it's in fact true that every even number is the sum of two primes. It gives us reason to expect that when we plug in an even number into our machine, we will get as output not 0, but 2 primes. Gödel's point here, and is going to be as we press on, is that if you don't have a realist interpretation of mathematics, that is to say, if you don't take the proof of Goldbach's conjecture to be a series of lines, each of which is, well, starts out with truths and is truth-preserving moves, so it gets you to a truth in the end. If you don't have anything like that, then you don't, and if all you have is simply syntactic manipulations that get you from a bunch of sentences to a sentence that expresses Goldbach's conjecture, then this proof gives you no reason to suppose that your machine will behave in a certain way. All you know is that that sentence is the output of an arbitrary stipulated system. You don't know anything about you don't know anything about the world, put it that way. One of the things you would need to know in order to be able to use your proof of Goldbach's conjecture as a reason to predict something about the world, one of the things you would need to know is that your system is consistent. If you don't know, it's not just that your system has to be consistent. It's that if you don't know that your system is consistent, then you don't know that the proof of Goldbach's conjecture is any reason to suppose that there isn't also a proof of the negation of Goldbach's conjecture. And of course, if you've got both of those, then neither of them gives you any reason whatsoever for predicting that your machine will behave in a certain way. On the other hand, from the mere fact that Goldbach's conjecture follows from some arbitrarily assumed rules for handling certain symbols, even if they imply the formalism of finitary arithmetic, okay, even if those rules give you the right sentences, nothing whatsoever can be concluded about the result the machine will yield. So let me try and be even more clear about this point. Suppose I've just designed a bunch of rules of syntactic manipulation for some radically different kind of purpose. Perhaps my purpose is to design rules which generate sentences that my sister likes from sentences that my sister likes, and she likes sentences that have particular patterns of ends, and right? Then there's no reason to suppose that that system of sentence generation, if it spits out Goldbach's conjecture, will give me a reason to predict that a machine will work in a certain way. Right? You need to know something about the rules of the system and what kind of properties they guarantee the proven sentences to have before you can use a proof as any grounds for a prediction about the empirical world. That, I take it, is the point. And one minimal requirement that you'll need to know about those rules, if you're not going to be all realist about it, right? If you're not going to say, well, a proof is just a series of claims that start with truths and go down to truths, that gives you a nice, easy, straightforward way of understanding how a proof gives you a grounds for an empirical prediction. If all you've got is the syntax, then you need to add something to that in order to know from a proof that you've got some reason for predicting something. And one of the things you'll need to know is that your system is consistent. You'll need to know more than that, I think, although Gödel does not stress this. I mean, frankly, as far as he's concerned, once he's established the fact that Carnap's program will require a consistency proof and that the consistency proof is impossible to give given Carnap's own requirements about mathematics, he's done. I think it's worth pointing out that a consistency proof wouldn't be enough. All right. And Gödel gives us two more examples, not just our machine prediction, but also a prediction about building bridges. The situation is quite similar for the prediction on the basis of empirically known physical laws that a bridge will not break under a certain load. And the third example he gives is an example in pure mathematics. It's not just empirical applications, right? Why should you think from a proof of some generalization that you can in fact solve a certain equation? And the question is, well, what would you need to know about your system of rules in order to be able to use the proof as a grounds for concluding something about future mathematics? And the answer is, well, at least consistency. Of course, by applying mechanically certain rules for handling symbols, one arrives at the same sentences as by using mathematical intuition, e.g. also at those sentences which express the two predictions, the one about the machine and the one about the bridge. However, mathematical intuition, in addition, that is to say our knowledge of the truth of what's expressed by the sentences, produces the conviction that if these sentences express observable facts and were obtained by applying mathematics to verified physical laws, then these facts will be brought out by observation. Therefore, syntax, if it's to be an acceptable substitute for mathematical intuition, must also yield sufficient reason for this expectation, and for this purpose, a consistency proof is necessary. I, the user of the system, need to know amongst other things, that it's consistent. And of course, Gödel's conclusion is, and I can't know that. So here is my summary of Gödel's objection number 2. A mathematical proof gives us reason to expect a particular empirically verifiable result when applied to an empirically confirmed generalization. If the rules of proof are arbitrary rules of syntax, then proofs give us no such reason. In order to obtain such a reason from such syntactic rules, one would need, in addition, the at least is my parenthetical, Gödel never says that, a consistency proof. But there can be no finitary consistency proof. And of course, all we're allowed, given Gödel's understanding of what the syntax project makes sense of, is finitary reasoning. Okay, so this then is, as far as Gödel is concerned, a reason for supposing that mathematics as understood in Carnap's way can make no sense of the applications of mathematics. I want to now talk about 2 responses one might make to this objection, and I think there are, I think there's a good deal of merit to each of them, but I do have some worries about them. So the first response is this. In order to justifiably use a mathematical proof as the basis of prediction, we don't need a proof of consistency, we just need a reasonable ground to believe that the system is consistent. And this we have in empirical induction. If it's a system that you've been using for a while and you haven't bumped into a contradiction, you might assume, as indeed we, I suppose, do, that the thing is consistent. So here, the idea is not that you know that your system is consistent, but you've got some reason to suppose it is, and that suffices for using a proof within that system as a reason that grounds an empirical prediction. Gödel himself, of course, considers this, and he has a response. And so, well, so I'm interested in this. As to the requirement of a consistency proof, it may be argued that, although transfinite mathematical axioms clearly must not be used, right, it is permissible. Why must they not? Because they don't fit into what Gödel understands as the syntax requirements on what a rule of proof might be. Okay. It is permissible to use empirical induction. For example, consistency might be based on the fact that no contradiction has arisen so far. And here's his objection, which I think is not as clear as it might have been. But if this empirical consistency is used, mathematical axioms and sentences completely lose their conventional character and rather become expressions of empirical facts. All right, so the worry is that if you use empirical induction, then something has gone wrong. You, in some sense, undermined the claim that your mathematics that you're using is purely conventional. Now, the first worry, it seems to me, that one might have, especially if one has read one's Ricketts, about this response, is that it's making exactly the same mistake that Tom Ricketts claims Gödel makes in what I called the first objection. So here's the question. Does this reply by Gödel make the same mistake as that pointed out by Ricketts in Gödel's objection number 1? And the mistake was, to remind you this, to suppose that Carnap relies on a language-independent notion of conventional or empirical. And let me just back up to show you again, right? If this empirical consistency is used, mathematical axioms and sentences completely lose their conventional character and rather become expressions of empirical facts. Okay. So I think, in fact, that Gödel is not making that mistake here. And here, I think, at least arguably, is what's going on in that, I think, somewhat obscure response to the let's use empirical induction suggestion. As the next thing Gödel does in the next few sentences is to point out that that various results, which looked, as it were, empirical or not mathematical, can be used to generate more mathematics, and so therefore they need to be counted as mathematical. And I think the lesson here is this, that the consistency statement, that thing that you were supposed to be grounding in empirical induction, that consistency statement is, of course, a mathematical statement. This is Gödel, as can be seen by its usefulness in deducing further mathematics. So if you're going to ground the consistency statement in empirical induction, then you're grounding a mathematical statement in empirical induction. And you're not just happening to ground it in empirical induction, you have to. It isn't a consequence, in the finitary sense of consequence, of the mathematical rules that you've gotten. So you now got a mathematical statement, which you're grounding in empirical induction, while out the other side of your mouth, you're saying all of mathematics is a finitary consequence of my syntactic rules. So that's the sense, I think, in which using an empirical induction, that is to say, I've been using this system for a long time, it seems consistent, therefore I reason it's consistent. That reasoning, I take it, is self-undermining in the context of Carnap's syntax program because the consistency statement is itself mathematical. Another response one might make to Gödel here. So this is on behalf of Carnap. You might agree that in order to make sense of the role of mathematical proof in providing grounds for empirical prediction, we do need a consistency proof. So agree that far. Forget response A. But deny that such a proof would have to be finitary. And this, let me say, is similar to a point again made by Tom Ricketts in, for example, his 1994 paper, which is this. Ricketts points out that while you would need to give a non-finitary consistency proof for, let's say, the system of language 2, in order to know that it were consistent, you don't need to know that it's consistent in order to know that it's a good system for doing, you don't need to know that it's consistent in order to know that its rules are conventions, in order to know that its mathematics is a bunch of syntax. And so the fact that you would need to, as it were, step outside of, let's say, language 2 and use a richer framework within which to prove the consistency of language 2 doesn't undermine the claim that language 2's mathematics is language 2's rules, because you're not using language 2's mathematics when you're proving the consistency of language 2. Okay? So you agree that a consistency proof would be non-finitary, but point out that that just shows that the mathematics of some other system is non-finitary, not that the mathematics of the system that you're interested in is non-finitary. Okay.
Say that again.
So.
Language 2 and what are the
Okay, so suppose we've, and here I hope I'm doing justice to Tom's point. It's this. If I wanted to know that the mathematics of, let's say, language 2 is consistent, I need to use a different framework. Why am I using a different framework? Because I'm using non-finitary rules. And the rules of language 2 and what follows from them has to be a bunch of recursively enumerable mathematics, basically. Well, okay, so here's the worry, that if Carnap doesn't think this, that, indeed not for Carnap, right? But one might worry that, here's the idea. One, I think, if one is Ricketts, is trying to save Carnap from the following serious problem, that if you're not agreeing with Gödel that the mathematics that follows logically from your stipulations has to follow in a recursively enumerable way, then you're employing mathematics to get mathematics out of your stipulations. This is arguably a Quinean objection. Forget Quine for a moment. So the idea was this, I think, to try and, as it were, save Carnap from himself and say, the mathematics that language 2 is concerned with is the rules of language 2. And what you can get out of them in a recursively enumerable, in a finitary way, let's say, by ordinary finitary reasoning. If you want to prove the consistency of language 2, you're going to have to do something else. You're going to have to use richer mathematics. But that's the richer mathematics of some other system. So we'll talk about that tomorrow, is the idea. Steve, do you think that's I noticed you nodding. Do you think that's a fair account of what's going on in this part of the dialectic?
If you want to prove things about language 2 involving like a truth definition, you need a different language to do it. And is that all you're saying? No,
so okay, so here, I have to say I'm a little bit of an awkward position here because I want to just grant Ricketts the point, though I don't in fact agree with him. But I wanted to grant the point just because it's more to argue with that has no bearing on my point, at least I think. But the idea was this: yeah, of course you have to move to a richer language. Does that engage one in a vicious circle? Now the vicious circle would be this: you have claimed, you Carnap, have claimed that all of mathematics, whatever that means, follows from the rules that you have laid down, right? These stipulations. But notice that if by follows from you mean something, as it were, non-question begging, something that doesn't already import more mathematics, then you're not going to get a consistency proof. You're also not going to get enough mathematics, but that's another aside. So the objection to Carnap is that using a richer system to prove the consistency of the system that you care about is problematic because now you're importing mathematics that violates your own claim that mathematics is all of it, what follows from the rules of syntax of your language. Okay, so I'm going to just leave this point. We can come back to it. Yeah, right. Okay. So here's response B. We agree that in order, and we deny that such a proof would have to be finitary. Right. And the basis of this denial would be that the consistency proof that uses non-finitary mathematics or non-finitary reasoning, however you want to think about it, that consistency proof isn't part of what you need in order to know that the mathematics of language 2 is a matter of the rules of language 2. That's sort of an external question, as it were. I don't think that this is a good response for someone who's defending Carnap to make. So the worries about response B being that a consistency proof can use a stronger system. As Gödel sees it, if the consequence relation isn't recursively enumerable, then it doesn't hold just in virtue of syntax, but it imports mathematics of a non-syntactic kind. So appeal to it is self-undermining, because the whole idea was that in order for me, the user of language 2, to be doing mathematics, I need to know that the system is consistent. I'm not even doing mathematics if I can't use the theorems that I prove in language 2 as a basis for empirical prediction. And I can't do that unless I have a good reason for thinking that the system is consistent. We've already rejected the idea that I might have a non-proof theoretic way of knowing that the system is consistent. So I'm going to have a proof of consistency that I can make sense of within the bounds of the mathematics that count as my system. And that's what I can't have. For both Frege and Gödel, what you're doing just isn't mathematics unless it justifies inferences of a certain kind. If you need to appeal to a stronger theory en route to those inferences, then we weren't, one way to put it, we weren't doing math in the first place. Your system wasn't a system of mathematics because it didn't make any sense of applications. Okay, and near the end. A further worry about applicability. This is something I was emphasizing earlier, so this will go quickly. Recall Gödel's claim that from the mere fact that Goldbach's conjecture follows from some arbitrarily assumed rules for handling certain symbols, nothing whatsoever can be concluded about the result the machine will yield. And this is when I told the silly story about, suppose the rules were for some arbitrary pretty reason. If you don't know anything about the rules, then you cannot use proofs as a basis for any kind of prediction. And this, I take it, is Frege's point as well. Notice that we would need, I believe, more than a mere proof of consistency in order to remedy this defect. That is, as an aside. Okay, let me just conclude by trying to sum things up. It seems to me that within the confines of the project of logical syntax of language, there's something about consistency that we want to know. And the question is what exactly? And I've tried to list these as what I've called 3 grades of consistency requirement for a good framework within which to do mathematics. The minimal requirement, it just has to be consistent. A slightly stronger requirement, we have to have a good reason to believe that it's consistent. A considerably stronger requirement, perhaps we have to have a proof of consistency. And then one might wonder what kind of proof. Well, a weaker version of 3a, any kind of proof will do. And 3b, it must be a finitary proof. And by the time we're down to 3b, we've got a serious problem. Okay, so the 3 grades, again, I've listed up there. So here, if I can sum things up in a nutshell, one of the important points about applicability that I think Gödel is interested in is this, that if applicability is essential to mathematics, and that I think is something that Gödel and Frege share, in the way that both Frege and Gödel think, then number 1 is much too weak. Why? Because we need to be able to use our mathematical proofs as the basis for, as a reason for, as a justification for empirical predictions. And the mere fact that the system is consistent doesn't do that. I need to know that it's consistent. If Gödel is right about inductive reasoning, then number 2 collapses to number 3 for Carnap. What I mean by that is there aren't any other kinds of good reasons that don't undermine the syntax project, because the only other reason you might have, other than a proof of consistency, is well, I've been using this system for a while and I can conclude via empirical induction that it's consistent. That, if the argument I gave earlier is compelling, won't work from Carnap's point of view, because then, again, the worry was we're then using a piece of mathematics, namely the consistency proof, the consistency claim. We're taking a consistency claim to be grounded in something that mathematical claims cannot be grounded in from Carnap's point of view. And of course, if Gödel is right about syntactic consequence, then the proof must be finitary as math, if math is to be syntax, and then the project will not work. Thank you. If you're interested, these are the